So welcome to the introduction of our MATLAB toolbox, Oscillatory Burst Detector. This is an analytical tool for estimating the reliability of detection of oscillatory bursts in the local field potential, or LFP, and electroencephalogram recordings, or EEGs. In this video, we'll walk you through the three major steps of our workflow and demonstrate the usage of the graphical user interface using an example local field potential data. So let's get started. The first step involves characterizing the input, which is an LFP or EEG recording, and using our algorithm, we fit the power spectral density, or PSD, and decompose it into signal and background components. It's similar to a popular algorithm, fitting oscillations in 1 over F, or FOOF, which decomposes the PSD into periodic and aperiodic components, and fit the aperiodic component to a 1 over F curve. We then characterize burst properties such as statistics of amplitude peaks, number of cycles, and burst frequency. And all these characterization results are saved for further analysis. Moving on to the second step, synthesis allows us to generate synthetic LFP data based on the results obtained from the characterization step. By loading the previous characterization results, we can specify parameters for synthesizing the background component and oscillatory signal component. One crucial aspect of this step is optimizing the parameters for the amplitude peak distribution of burst atoms in the signal component. This optimization ensures that the synthetic data reproduces the amplitude distribution of the observed data accurately. We offer three candidate types of parametric distributions: gamma, log normal, and exponential. In general, the gamma distribution works well. To assess how good the fit is, we use metrics such as Kullback-Leibler divergence, or Jensen-Shannon divergence, where a lower divergence value indicates a better fit. In the final step, analysis, we evaluate the detection performance using the synthetic data generated in the previous step. We define the ground truth by specifying lower and upper bounds in the synthetic signal trace. And to assess the detection performance, we employ a receiver operating characteristic, or ROC curve, which shows the relationship between the detection threshold and the true and false positive rates. This analysis allows researchers to assess the reliability of the detection algorithm and fine-tune the threshold for optimal performance. By utilizing these three steps, researchers can gain a comprehensive understanding of their LFP data, generate realistic synthetic data, and evaluate the performance of their detection algorithms. All right, now let's demonstrate the usage of the GUI using some example data. So before we begin, make sure that you have the signal processing toolbox and the statistics and machine learning toolbox installed in your MATLAB environment. To download our MATLAB toolbox, visit our GitHub repository. Download it from this download zip button under the green code button. And once downloaded, launch MATLAB and install the app using the MATLAB app installer. You can go to the folder that you just downloaded and click this oscillatory burst detector.ml app install file. And once you double click that, it'll install the toolbox into your MATLAB. After it's complete, just click the Oscillatory Burst Detector app to run the GUI, and it will open for you. So now that we have the GUI open, let's load the example data provided. The example data we'll be working with is the gamma oscillation case, which is illustrated in figures 1, 2, and 3 of the associated paper, approaches to characterizing oscillatory burst detection algorithms for electrophysiological recordings. In the example data folder, you'll find a file called lfp-bla-gamma.mat. So if we open up MATLAB, you'll see that in the example data folder right here. First, we just want to load this into the MATLAB workspace. So you can just click the file and drag it into the command window. So once the data is loaded, we need to scale it from digital values to microvolts using the line of code given in the instructions. So if we paste that into the MATLAB command window, this will scale the data by multiplying it with the scaling factor represented by this variable scale. And in this case, we're converting the data to microvolts. The sampling frequency of the data is 1000 Hertz, which is provided as the variable fs. And the LFP data was divided into segments. LFP seg is a cell array with each element a segment of the LFP recording. It's important to note that gamma oscillation is present in this data. With the data loaded and scaled, we're now ready to proceed with the GUI. So to begin the characterization process, go to the Select Data panel, select the variable LFP seg in the LFP data section, and enter the sampling rate fs in the sampling rate field. Now let's move on to the Fit PSD panel. leave the default settings as they are, gamma oscillation frequency range of 30 to 80 hertz for the signal frequency band, auto fit for the frequency range for fitting, and 1 decibel for the decibel threshold. Once you set the parameters, click the fit button. I'll begin estimating the PSD. As you proceed, the figure displaying the PSD fit will appear on the top right of the GUI, and messages related to the process will be printed out in the results section at the bottom. After successfully fitting the PSD, it's time to characterize the bursts, and the characterized burst and fit probability distribution panel use the default settings, so 30 for the number of histogram bins and microvolt as the unit for the LFP amplitude, and we click on the Run button to proceed. Now there's 2 options buttons, and you can click those for more settings, but we won't go into those in this video. Now the figures for the histograms of the burst attributes will appear on the bottom right of the GUI, and you can select different tabs on the right side to switch between attributes such as the amplitude peak, cycle number, and burst frequency. And moreover, you can select the tabs at the bottom to switch between linear and log scale for the histograms. So now that we've obtained the characterization results, it's essential to save them for future reference. So in the project directory panel at the top of the GUI, you want to select or create a folder where you want to save all the results for this example LFP data. So I'm going to use a folder titled results. Then we want to enter the name of the data, such as LFP BLA gamma, and the text box located in the Save Characterization Data section at the bottom. And finally, we want to click the Save button, and the results will be saved to a MAT file named LFP BLA gamma underscore charac for characterization.mat in the selected folder. And if you want to save the attribute values of each burst, we want to check the box that says Also Save Burst Statistics before clicking on the Save button. This will create another MAT file named LFP BLA gamma burst stats.mat in the same folder. We click Save, and we'll save both of these files into the results folder. So now we've successfully completed step 1 using the GUI. The characterization results are now saved, and we're ready for the next step. To begin the synthesis process, we want to select the tab at the top of the GUI to switch to step 2. And the characterization data panel, you should see the characterization result file that was saved from step 1. But if not, you can manually select the file using the Select File button. In the synthesis settings panel, leave the default sampling rate for the synthetic signal, which should be the same as the LFP data. And in the RNG seed field, you can enter any random seed number, for example, 0. Then we want to click the Load button. This will load the results from step 1 and create the necessary settings for generating the synthetic data. The next step is to optimize the amplitude distribution and the synthetic data using particle swarm optimization. And the Optimize Amplitude Distribution Parameters panel, select the default synthetic data length, which is 1,000 seconds. You can also select the parametric distribution types for the amplitude of the burst atoms to be generated. The default type is gamma, but you can select multiple types by using Control-Click in the menu. So here we can select all 3. Additionally, you can change the population size of the PSO algorithm by selecting the distribution type in the drop-down menu and entering the desired number. So for instance, we can change for gamma, log normal, and exponential. A larger population size allows for a broader exploration of the search space, but increases the runtime per iteration. Finally, choose the amplitude peak option for the fit target, which considers only the peak of the amplitude. Click on the Fit button to run the optimization process. And just note that it may take several minutes to complete, but once finished, the amplitude distribution plot of the synthetic data and the observed data will be displayed on the right side. So now the optimization is complete. Just took a few minutes. The next step is optional. It involves generating the synthetic LFP and displaying its PSD and burst statistics for comparison with the observed data. So in the Generate Synthetic LFP panel, you can choose a synthetic data length, which will affect the accuracy of the analysis in step 3. You can also choose a distribution type for the burst atom amplitude if you have run the optimization with multiple types. Once you've made your selections, click on the Run button to generate and display the synthetic LFP. So we can just click Run with the default and using gamma as a distribution type. So finally, you need to save the synthesis parameters for step 3. So we'll click on the Save button to save a MAT file with the synthesis parameters, but it must be saved in the same directory as the characterization result file. So make sure that you CD to the result file that you created earlier. So in this case, we went to results, where we had the files we saved in the previous steps. The default name for the synthesis parameter file is LFP BLA gamma synparam.mat, unless you specify a case name, which is useful when there are multiple sets of synthesis parameters you want to keep. So we can save this file, synparam.mat. But if you want to save the synthetic LFP that was generated previously, we can check the box also save synthetic LFP. And when we click the save button, this will create a mat file named LFP BLA gamma syndata.mat. The file could have a large file size, but it saves time to regenerate the data in step 3. So let's save that. So now we've saved these 2 files into the results folder. And if we go to the files, we can see that the syndata.mat file is much larger in size than the parameters, but it's useful for saving some time in the next step. So now we've successfully completed step 2, synthesis using the GUI. The synthesis parameters and optionally the synthetic LFP data are now saved, and we're ready for the next step. So to begin the analysis process, select the tab at the top of the GUI to switch to step 3. In the synthetic data panel, you should see the file saved in step 2 automatically, but if not, you can manually select the file using the select file button. If you need to review or modify the optimization results in synthesis parameters, you can click on the review settings button, and the GUI will switch back to step 2. There you can change the settings or rerun optimization if needed, and any changes you make will be effective for step 3 once you click the run button in the generate synthetic LFP panel. So once we have the synthetic data, we can just load it in. In the pre-selected bounds panel, you can define the lower and upper amplitude bounds in the synthetic signal trace, which defines salient oscillatory events that serve as the ground truth for evaluating the detection. These bounds can be specified using either an absolute amplitude value or a multiple of sigma, which is the square root of the average power in the noise trace. By default, the lower bound is square root of 2 times sigma, and the upper bound is determined based on the decibel threshold and the PSD. Once the bounds are determined, click on the Select Bounds button. The resulting ground truth information will be displayed in terms of the time duration proportion and the amplitude peak rate in the proportions for each category. In the Detection Performance and ROC Curve panel, leave the default settings. The number of thresholds is set to 50, and amplitude peak is the target for detection. Then click on the Evaluate button. The ROC curve will be displayed on the top right, and the distribution of the ground truth will be displayed on the bottom right. You can adjust the detection threshold by entering a z-score of the amplitude or using the slider with an absolute amplitude scale. The resulting false positive rate will be shown in the text box and on the slider below. The corresponding operating point will be marked on the ROC curve, and the threshold will be displayed as a vertical line in the distribution plot. So here's what it looks like as we change the slider. The conditional probability given a detection panel shows the probability of each true outcome given a detection with an amplitude greater than the threshold. For example, using a 1 z-score detection threshold, if an amplitude peak above it is detected, there's an 11.8% chance of it being a false positive and an 88.2% chance of it being a true positive. These probabilities correspond to the areas under the distribution curve to the right of the detection threshold. You can select equals to threshold in the drop-down menu to show the conditional probabilities given a detection with an amplitude exactly equal to the detection threshold. These probabilities correspond to the proportion of each segment length along the vertical line of the detection threshold in the distribution plot. In addition, you can set a false positive rate by entering a value in the text box or moving the slider. The corresponding detection threshold will be displayed above it, and the figures will update accordingly. The maximum mutance index is a method that determines the optimal detection threshold by maximizing the difference between the true positive rate and the false positive rate. The operating point corresponding to the maximum mutance index will be marked on the ROC curve, and the optimal detection threshold will be printed in the results section at the bottom of the GUI. Now you've successfully completed step 3, analysis using the GUI. The ROC curve, conditional probabilities, and optimal detection threshold provide valuable insights into the performance of the detection. So thank you for following this tutorial on the Oscillatory Burst Detector Toolbox. We hope you found it informative and helpful for your research, and we invite you to explore it further and enhance your work with our toolbox. Thank you.